Hello, I'm Kara Tierney from Monroe Community College, and we're going to talk about molecular polarity today. Now, in order to talk about molecular polarity, I want to do a review of electronegativity and bond polarity. So if you recall, electronegativity is the relative ability of a bonded atom to attract the shared electrons. So when we look at two covalent bonds that are between two different atoms, the electronegativity of the atoms can affect the properties of the bond. So when we look at a bond between two hydrogens, those electrons are evenly shared because both of those atoms have the same electronegativity. When we look at a bond between hydrogen and chlorine, chlorine has a higher electronegativity, so those electrons will be drawn towards the chlorine more than the hydrogen. And here I have the chart of the values for electronegativities. Once again, you don't need to memorize this chart, but do know the relative values and trends. So we know that fluorine, for instance, has the highest value. Now, when we look at a polar versus a nonpolar covalent bond, let's just review these definitions. So a nonpolar or pure covalent bond has both atoms equally sharing those electrons. This occurs between atoms of either equal electronegativities or very close electronegativities. The electron cloud around the two nuclei is very even because that means that the electrons are spending equal amounts of time around both of those atoms. So, for example, in our hydrogen bonded to hydrogen, we would draw the electron cloud as a nice even cloud around both of them. The electrons don't spend more time with one atom over the other. In a polar covalent bond, the opposite happens. We have unequal sharing of electrons because one atom is more electronegative than the other. When you have a larger difference in electronegativity values, then you have more polarity of your bond. So because chlorine is more electronegative than hydrogen, these bonded electrons are going to spend more time around the chlorine, giving this bond a distorted electron cloud. It's bigger around the chlorine because those bonded electrons are going to spend more time there. And what this does is it leads to partial charges because if there are electrons spending more time around the chlorine, there's going to be a partial negative charge, and we call that the negative pole. Around the less electronegative atom, the electron that it used to have now doesn't spend as much time there, so we have a partial positive charge. This is referred to as the positive pole. So we can designate these partial charges or the poles in a couple different ways. If you want to use the arrows, we can draw an arrow right near our bond with an arrow, the arrow pointing towards the more electronegative atom, and a plus sign on the end near the less electronegative atom. We can also draw the partial charges, which we use the symbol delta for partial. So we put a partial negative near our more electronegative atom and a partial positive near the less electronegative atom. And so we're going to use these designations as a way to determine molecular polarity. So this is determining the polarity of a molecule that has multiple bonds. And when you have a polar molecule, that is a molecule that has a net imbalance of partial charges. So this is referred to as a dipole moment when you have an uneven distribution of partial charges. And what it means is you have one area of the molecule that is partially positive and one area that is partially negative. And so much like with the polar bond, we now have a positive pole and a negative pole, but now this is of an entire molecule. A nonpolar molecule has no net dipole. This can occur one of two ways. Either all of the bonds that make up that molecule are nonpolar themselves, so they don't have any partial charges, or more commonly, you have polar bonds that are arranged in such a way that the partial charges are evenly distributed. And so there's no one area of the molecule that is partially negative as compared to another area that's partially positive. So how do we determine the polarity of a molecule? This is just kind of an introduction, but the nitty-gritty, the steps that you need to take are what we're going to talk about right now. So in order to determine the polarity of a molecule, the first thing you need to do is draw a Lewis structure. You need to make sure that you are successful in drawing Lewis structures. Same with the next step is just a review of something that we've learned in class. Once you've drawn the Lewis structure, now you need to determine the molecular geometry and draw the 3D sketch of the molecule. It's very important that you are solid in being able to do these first two steps, which we recently learned in class. Once you have the 3D sketch of the molecule drawn, now what you're going to do is you're going to indicate the partial charges or the dipoles of each of the polar covalent bonds within that molecule. Now it's very, very important that when you draw arrows or partial charges that you do not do that on a Lewis structure. You must draw it on the 3D sketch. I would highly advise putting a star next to that or underlining it. It is one of the most common mistakes that students will make in determining the polarity of a molecule. So once you've drawn your arrows or partial charges, and honestly you can do either, I'm going to show you how each of them will lead you to the correct conclusion. I just want you to use the one that's most comfortable for you. So once you've done that, if you have a nonpolar molecule, if you drew the partial charges, so the delta symbols, you're going to look for whether you can divide those partial charges into one area being positive and one area being negative. If you can't divide that molecule, then you have a nonpolar molecule. If you can divide the molecule into a partial positive area and a partial negative area, then you have a polar molecule. If you want to draw the dipole arrows, then what you're going to do is you're going to add them like vectors. So if you are familiar with the physics concept of drawing and adding vectors, this might be a very familiar technique for you. So if you're adding the arrows like vectors, then you're going to see for a nonpolar molecule, there's no net result. And that's because there's no dipole, there's no overall dipole for a nonpolar molecule. What we see for polar molecules is that they can be divided into a partial negative side and a partial positive side, and that when we add up the arrows, the dipoles, we see that there is an overall dipole arrow for the entire molecule. If you're not familiar with vectors, that's okay. We can also think of it as kind of a tug of war game. In the nonpolar molecules, when all of those arrows are either pointing in or out, you can think of them pulling in or out. If there's no winner for that tug of war game, then you have a nonpolar molecule. If there is a clear winner, then you have a polar molecule. So there's a few different ways to think about this, and I'm going to do my best to talk about all of them as we go along. But you might want to think about which one works best for your brain. And I just want to add that the presence of polar bonds does not necessarily lead to a polar molecule. So in a nonpolar molecule that's made up of polar bonds, what happens is these polar bonds do something that we call cancel out. So the most clear way to see polar bonds canceling out is in a linear molecule. So let's say we have a molecule with A as our central atom and B as our two terminal atoms, and we have a linear molecule. If we were to draw arrows for this, then we see that the two arrows, if B is more electronegative than A, we would have two arrows pointing out. If we were to add those together like vectors, we would see there would be no resulting vector. If we were to think of it as a tug of war game, there would be no winner because they're both pulling out in the opposite directions. So this would indicate that we have a nonpolar molecule. Those two bonds are canceling out. If you prefer to draw the delta symbols, let me show you what that would look like. So we would put partial negatives near our B because it's more electronegative. and partial positive near A, and we see that the partial positive is exactly in between the two partial negatives. There's no way for me to divide the partial positive from the partial negatives with just a single line. And so that's another way that we can determine that this molecule is nonpolar. And this is nonpolar even though it's made up of two polar bonds, because those two bonds cancel out. Let me show you a couple other ways in which bonds can cancel out. So if we have, like in our leftmost molecule, a trigonal planar molecule, if, once again, we have a central atom surrounded by terminal atoms that are all the same, let's say that this terminal atom is more electronegative once again. If we were to draw partial negatives around all of them, and we put our partial positive here near our central atom, we'll see that the partial positive is exactly in between all of the negatives. There's no way to divide out a partial positive from a partial negative. You can also think of it with our arrows. We would have three arrows, and now this canceling out is not as obvious, but you would see if we had like a tug of war game that there would be no winner because all three are symmetrically around that. So we would see that with a tetrahedral shape as well as octahedral shape. In all of these, if we had the same terminal atom completely surrounding our central atom, then we would have no clear winner to these tug of war games. Okay. Now I know that this becomes less and less obvious as our shapes become more complex, and I understand that, and that is why we are going to spend some good time in class doing examples, because this will take some practice to get. And so what we're going to do in the next video is we're just going to be practicing determining when bonds cancel out, when they don't, how we determine polarity. So this is not the last you will see this. So in our next video, we're just going to do some examples to get you more comfortable with this process. And I'll see you there.